A colossal storm has raged for centuries on a world with no solid ground. This is Jupiter, the king of our solar system, a gas giant swirling with secrets that defy our basic understanding of planets. By the end of this journey, you will know 25 of its most profound and unanswered mysteries. We will explore a planetary interior that should not exist, moons hiding global oceans, and a magnetic field with a bizarre dent. Each discovery from probes like Juno only deepens the wonder. What does it feel like to realize we are only beginning to comprehend the giant next door? That persistent crimson eye staring back at telescopes for centuries is our first great puzzle. The Great Red Spot is not merely a storm. It is an atmospheric monster, a hurricane wider than our entire planet that has been spinning for at least 200 years and likely far longer. Think about the most powerful hurricane ever recorded on Earth. Its fury is measured in days, perhaps a couple of weeks, before it runs out of warm ocean water and tears itself apart over land. Jupiter has no ocean, and it certainly has no land. The Great Red Spot feeds on something far more enigmatic, the internal heat of Jupiter itself and the complex shearing winds of its atmosphere. It is a self-sustaining vortex locked in a band of wind flowing in the opposite direction of its neighbors, a rolling, high-pressure maelstrom that simply refuses to die. For decades, we watched it slowly shrink, leading to whispers that the giant was finally fading. Yet, recent observations suggest it may be stabilizing, even deepening. Its color shifts from a faint salmon pink to a deep, ominous brick red, changes we think might be linked to chemicals being dredged up from far below the cloud tops by the storm's powerful winds. Is this storm a permanent fixture of Jupiter, as integral as its stripes, or are we witnessing the long, slow death of a legend, a process that takes centuries to complete? The truth is, we do not know what ultimately powers its endless rage or what will finally make it stop. Yet the Great Red Spot is just the surface of a much deeper enigma. To truly understand Jupiter, we must venture below those churning clouds into a realm of unimaginable pressure where matter itself behaves in alien ways. For generations, astronomers pictured Jupiter with a relatively simple interior. They imagined a small, dense, solid core of rock and metal, perhaps 10 or 20 times the mass of Earth, buried at the very center. Above it, a vast ocean of metallic hydrogen, a form of hydrogen so compressed it conducts electricity like a metal. And above that, the outer layers of liquid and gaseous hydrogen that we see as the striped atmosphere. This was the classic layered model, a cosmic onion with a solid heart. Then the Juno spacecraft arrived. By measuring the subtle wobbles in Jupiter's gravity field with incredible precision, Juno gave us an X-ray vision of sorts, allowing scientists to map the distribution of mass deep within the planet. The results were shocking. The data did not point to a small, compact core sitting neatly at the center. Instead, it suggested something far stranger, a diluted or fuzzy core. Imagine taking that classic dense ball of rock and metal and stirring it vigorously into the surrounding soup of metallic hydrogen. The heavy elements are not concentrated in a distinct sphere. They are spread out over a region nearly half of Jupiter's radius, mixing and blending with the lighter hydrogen and helium. It is as if the planet's heart has dissolved. This presents a monumental puzzle for how giant planets form. The leading theory says a gas giant begins with a solid core of ice and rock. Once this core grows massive enough, perhaps 10 to 20 Earth masses, its gravity becomes strong enough to rapidly pull in the vast amounts of hydrogen and helium gas from the early solar system, ballooning into the giant we see today. But if Jupiter's core is not solid and distinct, how did it ever gather that gas in the first place? Did it have a solid core that was later shattered and mixed by a cataclysmic impact with another planet-sized object? Or does the formation process itself, with materials crashing into the young Jupiter at tremendous speeds, create this fuzzy, extended core from the very beginning? Jupiter's missing, or rather dissolved, core forces us to question the very blueprint for building a giant planet. It suggests that the interior of a gas giant is not a quiet, orderly place of neat layers, but a dynamic, churning cauldron where the very ingredients of a world are forever being mixed. What other secrets are hidden in that diluted heart? This churning, dynamic interior may hold the answer to another fundamental mystery. Jupiter radiates an astonishing amount of energy back into space. In fact, it emits nearly twice the heat it receives from the Sun. This means the planet generates a tremendous amount of internal warmth, glowing like a faint, slow ember in the dark. For a world that is not massive enough to ignite nuclear fusion and become a star, this presents a thermal puzzle. Where does all this extra heat come from? The leading explanation is a process called gravitational contraction, often described by the Kelvin-Helmholtz mechanism. Imagine Jupiter as a colossal ball of gas that is still, very slowly, collapsing under its own immense weight. As the gas compresses, gravitational potential energy is converted into heat. Think of it like pumping air into a bicycle tire. The pump gets warm because you are compressing the air inside, converting your effort into thermal energy. Jupiter has been doing this on a planetary scale for billions of years, shrinking by perhaps a millimeter or two each year as it gradually settles. The heat from this incredibly slow squeeze works its way up from the deep interior, driving the turbulent weather we see at the cloud tops. But is this process efficient enough to account for all the heat we measure? Some scientists suspect it is not. There could be other furnaces stoking Jupiter's warmth. One compelling idea is helium rain. Deep within Jupiter, where pressures are millions of times greater than Earth's atmosphere, hydrogen is squeezed into a metallic liquid. In this exotic environment, helium may not mix perfectly. Instead, it could condense into droplets like rain forming in a cloud. These droplets of denser helium would then fall inward toward the planet's center, releasing gravitational energy as they descend, creating additional heat. This internal precipitation could be a continuous source of warmth. Other theories point to powerful deep atmospheric currents, or even the slow sinking of heavier elements from that fuzzy core as potential heat sources. The truth is, we are still piecing together the planet's thermal budget. This internal heat engine is not just a curiosity. It is the very power source for Jupiter's spectacular and violent weather, driving winds that can exceed 400 miles per hour. Without it, those iconic stripes and the great red spot itself might fade into a much calmer and far less mysterious atmosphere. So the question remains, is Jupiter's warmth simply the last sigh of its formation, or is it fueled by an ongoing, hidden meteorological drama deep within its liquid heart? That internal heat churning within Jupiter does more than just power storms. It also generates a force field of almost unimaginable scale. Jupiter's magnetic field is the largest single structure in our entire solar system. If you could see it glowing in the night sky from Earth, it would appear larger than our full moon, a vast, invisible bubble that stretches for millions of miles, sweeping past the orbits of its largest moons. This magnetosphere is a fortress, deflecting the deadly solar wind and trapping charged particles in intense radiation belts. But as the Juno probe dove through this invisible realm, it discovered the fortress is built on a strange and lopsided foundation. Jupiter's magnetic field is profoundly asymmetrical. It is far stronger in the northern hemisphere than it is in the south. This is nothing like Earth's magnetic field, which, while it has its own quirks, is roughly symmetrical between its two poles, like the field around a simple bar magnet. Jupiter's field looks like it was assembled by two different blueprints. One leading theory points directly to the chaotic interior we just explored. On Earth, our magnetic field is generated by the churning of molten iron in the outer core, a relatively orderly process happening in a spherical shell. Jupiter's field is born in a different ocean entirely, its vast sea of metallic hydrogen. This is not a calm, uniform layer. It is a realm of violent, turbulent convection, where material heated by the planet's deep interior rises, cools, and plunges back down in colossal, chaotic cycles. Scientists suspect this turbulence is not evenly distributed. The convection might be more vigorous or organized in the northern hemisphere of that metallic hydrogen layer, creating a more powerful and concentrated dynamo action there. Imagine trying to generate electricity with two different engines, one running at full throttle and the other sputtering. The result would be an uneven, lopsided power output. That appears to be what is happening deep inside Jupiter. The planet's magnetic field is not a neat, simple dipole anchored at the center. It is a complex, messy, and intensely powerful phenomenon that is literally shaped by the stormy weather occurring thousands of miles below the cloud tops in an ocean where hydrogen flows like a liquid metal. This asymmetry has real consequences, funneling intense radiation differently around the planet and creating a magnetic environment that is not only vast but bizarrely warped. What other surprises are hidden within the contours of this invisible, lopsided giant? The lopsided nature of Jupiter's magnetic fortress is not its only peculiar feature. There is a profound weakness in its defenses, a strange dent near the planet's equator. This is not a small flaw. It is a major indentation where the magnetic field, which should be arching powerfully out into space, instead sags inward, creating a vulnerable spot in the magnetosphere. Think of it like a dent in a suit of armor. Everywhere else, the solar wind, a constant stream of charged particles from the sun, is deflected safely away. But at this equatorial dent, those particles can push the magnetic field lines closer to the planet, allowing energetic radiation to penetrate deeper into Jupiter's inner space than anywhere else. What could cause such a significant deformity in a field generated thousands of miles below the clouds? The prime suspect is Jupiter's own atmosphere. The planet's powerful east-west jet streams, those bands that create its striped appearance, may be interacting with the magnetic field in a way we are only beginning to understand. The theory suggests that these deep atmospheric winds, flowing in alternating directions, create electrical currents within the planet's interior. These currents, in turn, can distort the magnetic field being generated below, essentially pushing it out of shape from the inside. It is as if the turbulent weather we see on the surface is reaching down and leaving a fingerprint on the planet's invisible force field. This dent has dramatic consequences. It is a funnel for charged particles, directing them toward the polar regions where they collide with the atmosphere to create Jupiter's spectacular, permanent auroras. These are not like our fleeting northern lights. They are planet-sized rings of brilliant radiation, hundreds of times more energetic than Earth's, and they are fed in part by this magnetic vulnerability. The dent also means the radiation environment around Jupiter is even more complex and hazardous than we thought, with pockets of intense particles where our models did not predict them. This feature reminds us that a gas giant is not a set of separate systems. Its weather, its deep interior, and its magnetic personality are all woven together into one chaotic, interconnected whole. A storm on Jupiter does not just blow clouds, it might literally bend the space around the entire planet. This invisible, lopsided magnetic field shields a world built from the primordial ingredients of our solar system, yet one of its most basic components remains a profound puzzle. For decades, scientists have struggled to answer a seemingly simple question: how much water is in Jupiter? You might think a planet made mostly of hydrogen and helium would have a straightforward answer, but water, or more precisely, the oxygen bound within it, is a crucial tracer of the planet's formation history. Early theories suggested Jupiter should be relatively wet, having formed in the colder outer solar system where water ice was abundant. However, the first measurements from the Galileo probe in the 1990s delivered a stunning surprise. When it plunged into a seemingly typical patch of Jupiter's atmosphere, it found the air to be surprisingly dry, with far less water vapor than expected. This single data point suggested Jupiter might be a desert world, a finding that threw planetary formation models into disarray. If the largest planet, which should have acted as a gravitational vacuum cleaner for all the surrounding material, was dry, what did that say about the delivery of water to Earth and the other inner planets? For years, this mystery festered, a single measurement casting a long shadow over our understanding. Then came Juno. Equipped with a microwave radiometer, Juno did not just take a single sample. It peered deep below the cloud tops across many latitudes, mapping water abundance by sensing thermal radiation from within the atmosphere. Its findings revealed a far more complex and interesting picture. The water content is not uniform at all. Preliminary data suggests the atmosphere may be much richer in water near the equator, while remaining drier at other latitudes. This uneven distribution points to a dynamic, churning world where ingredients are not fully mixed, perhaps with powerful downdrafts of dry air from higher altitudes suppressing water vapor in some regions, and upwellings from the deep interior enriching others. The global average remains elusive, a moving target hidden by Jupiter's fierce weather. Pinpointing Jupiter's true water abundance is not just about quenching our curiosity. Water, along with other volatile compounds like ammonia and methane, were the building blocks delivered to the inner solar system by asteroids and comets. Jupiter's composition is a frozen record of that delivery service. By measuring its water, we are essentially taking a core sample of the early solar system's inventory, understanding what raw materials were available when planets like our own were assembling. Does Jupiter hold a vast, hidden reservoir of water deep within, or is its distribution a testament to a chaotic and uneven birth? The answer will rewrite the story of how our own world got its oceans. While Jupiter's water content hints at its deep history, its poles reveal a meteorological artwork of breathtaking precision. Before Juno arrived, no one knew what lay beneath the planet's thick bands of cloud at its extreme north and south. The spacecraft's first polar flyby revealed a sight unlike anything else in the solar system. At the North Pole, 8 colossal cyclones swirl in a perfect octagon around a single central cyclone. At the South Pole, 5 equally massive storms form a stable pentagon, again encircling a central vortex. Each of these cyclones is a permanent hurricane, as wide as the continental United States, and they are locked in this stunning geometric arrangement with no sign of drifting or merging. This is not a temporary phenomenon. It is a permanent feature of Jupiter's polar weather, a clockwork of storms that defies our basic understanding of fluid dynamics. On Earth, when 2 hurricanes get close, they either dance around each other in a complex waltz or merge into a single, larger system. They do not settle into a stable, evenly spaced polygon and stay that way for years. So what force is acting as the cosmic traffic cop, keeping these atmospheric titans in their precise lanes? The answer likely lies far below the visible cloud tops. One compelling theory suggests these cyclones are not shallow weather patterns, but deep-rooted structures. They may be anchored to powerful jet streams or convection plumes rising from Jupiter's deep interior, acting like atmospheric pilings driven into the planet's fluid layers. Another idea points to the powerful Coriolis force generated by Jupiter's rapid rotation. This force, which deflects moving objects on a spinning planet, could be creating zones of stability between the storms, forming invisible barriers that the cyclones cannot cross. Think of it like trying to push 2 powerful magnets together with the same poles facing. A repulsive force keeps them apart. The geometric shapes themselves, the pentagon and octagon, might be the most stable configurations for that number of vortices under Jupiter's specific polar conditions. It is a natural experiment in planetary fluid dynamics operating on a scale we could never replicate. These permanent polar polygons are more than just a beautiful mystery. They are a window into the deep, organized chaos of a gas giant's heart, revealing a level of atmospheric order we never dreamed could exist amidst the fury. These perfect polar storms exist within a cosmic environment littered with the debris of the solar system, and Jupiter's immense gravity has swept up much of it. This scavenging has created a feature most people never associate with the king of planets, a ring. Not the brilliant, icy spectacle of Saturn, but a ghostly, dusty halo that whispers of hidden violence. Jupiter's faint ring system is a mystery of persistence, a delicate structure that should not last long in such a chaotic gravitational neighborhood. The rings are not made of bright, reflective ice like Saturn's. Instead, they are composed of incredibly fine, dark dust particles, so tenuous that they were only discovered when the Voyager 1 probe looked back at Jupiter against the darkness of space in 1979. They are primarily maintained by a constant, brutal bombardment. Jupiter's small inner moons, like Metis and Adrastea, orbit within the most intense region of the planet's radiation belt. This space is a shooting gallery of micrometeoroids, tiny specks of rock and ice hurtling at tremendous speeds. When these particles slam into the surfaces of these moons, they do not simply create craters, they blast clouds of dust off into space. This ejected dust then becomes trapped in orbit around Jupiter, slowly spreading out to form the main ring we see. It is a system built from continuous destruction, a halo of pulverized moon dust. Yet this explanation, while elegant, leaves profound questions unanswered. The detailed structure of the rings is more complex than a simple, even sheet of dust. There is a faint, extended outer gossamer ring linked to the moons Thebe and Amalthea, and the main ring has a puzzling, sharp outer edge that aligns perfectly with the orbit of the small moon Adrastea. How does this tiny moon act as such an efficient shepherd, keeping the ring's particles neatly confined? Furthermore, the dust in these rings is constantly being lost. It spirals inward toward Jupiter under the influence of its powerful magnetic field, or gets pushed out by the pressure of sunlight. The bombardment from micrometeoroids must therefore be a relentless and perfectly balanced process, replenishing the dust at exactly the same rate it disappears. Is the current rate of impacts enough to sustain the rings we see today, or are we witnessing a temporary structure that is slowly fading? The rings are a living record of the ongoing demolition happening at Jupiter's doorstep, a delicate balance between creation and annihilation that we are only beginning to measure. Those ghostly rings are a testament to the constant, unseen collisions shaping Jupiter's domain, but the planet's most famous feature hides a thermal contradiction of its own. The Great Red Spot is not just a storm of unimaginable scale, it is also a bizarre atmospheric heater. While the swirling cloud tops of the vortex are bitterly cold, shrouded in high ammonia ice clouds at temperatures around -260 degrees Fahrenheit, something extraordinary happens far above them. The upper atmosphere, hundreds of miles above the storm, is a blistering hotspot. Instruments have detected temperatures there soaring to over 1,400 degrees Fahrenheit, hundreds of degrees hotter than the surrounding atmosphere at the same altitude. This creates a stunning vertical paradox, a cold storm casting a pillar of intense heat into the sky above it. How can a frigid vortex act like a cosmic fireplace? The energy must be coming from below, from the turbulent chaos of the storm itself. Scientists believe the key lies in atmospheric waves. As the Great Red Spot churns, it acts like a colossal stone in a river, disturbing the flow of the atmosphere around and above it. It likely generates powerful acoustic or gravity waves, ripples of pressure and density that travel upward, carrying energy from the lower, turbulent atmosphere into the thin, high layers. When these waves break, much like ocean waves crashing on a shore, they dump their immense energy into the upper atmosphere as heat. It is a form of atmospheric sound heating, where the roar of a silent storm is converted into thermal energy miles above the clouds. The Great Red Spot, therefore, is more than a vortex. It is a unique planetary-scale heat engine, a machine that takes the chaotic motion of a storm and transforms it into a sustained thermal anomaly visible from Earth. This process is not fully understood on Jupiter, and it hints at a complex vertical connection between a planet's deep weather and its outer atmospheric shell that we are only beginning to map. What other invisible energy pathways are hidden within the storms of the gas giants? The immense heat rising from Jupiter's storms fuels a kind of weather we thought we understood, but in an utterly alien form. High above the cloud decks, in regions once thought to be serene and frozen, the Juno spacecraft witnessed sudden, brilliant flashes. This was lightning, but not as we know it. On Earth, lightning is born in clouds where water exists in all three phases: solid ice, liquid water, and vapor. The collision of ice particles and water droplets builds up the electrical charge that eventually discharges in a dazzling bolt. For Jupiter, scientists always assumed the same process must be happening, but deep down where temperatures are warm enough for liquid water to exist. Juno's instruments revealed something astonishing. These new flashes were occurring high up in the atmosphere, far above the water clouds, in zones so cold that pure water could only exist as ice. How could there be lightning in a place with no liquid water? The answer appears to be a compound that acts as a planetary antifreeze, ammonia. The theory suggests that powerful thunderstorms dredge up water vapor from the deep, warm interior. As this moist air rises, it meets ammonia vapor diffusing down from higher altitudes. In the cold upper atmosphere, the ammonia dissolves into the water ice crystals, dramatically lowering their freezing point. This creates a bizarre, slushy mixture of water and ammonia, a kind of half-frozen mush that can exist in a liquid-like state at temperatures as low as -100 degrees Fahrenheit. Within these frigid, ammonia water clouds, the same charge separation process can occur. Ice crystals and slushy droplets collide, building up tremendous electrical potential until the sky erupts with what scientists now call shallow lightning. This discovery solved one mystery only to unveil a stranger one. What happens to all that ammonia water slush? It does not stay aloft. These mixtures can grow into large, mushy hailstones, which Juno's team nicknamed mushballs. Heavy with ammonia and water, these mushballs plunge downward into the deeper atmosphere like exotic precipitation. As they fall into warmer layers, they eventually evaporate, releasing their ammonia and water vapor back into the air. This process creates a previously unknown global weather cycle, a kind of ammonia-based rainfall that efficiently transports these chemicals from the upper atmosphere down into the planet's hidden depths. It is a complete reimagining of atmospheric physics. Jupiter's thunderstorms are not just bigger versions of our own. They are alien chemical engines, brewing exotic precipitation in clouds of antifreeze and sending mushy hail on a journey into the eternal night below. But the strange weather of Jupiter's atmosphere is nothing compared to the cosmic junkyard orbiting the planet itself. Beyond the four famous, world-sized Galilean moons lies a hidden realm of misfits and wanderers, dozens of small, irregularly shaped satellites tumbling through space. These are not smooth spheres like our own moon. They are jagged, lumpy, and often potato-shaped, looking more like asteroids than proper moons. Their very existence and bizarre forms are a direct window into the violent, chaotic construction site the early solar system once was. The leading theory is that most of these small moons are captured asteroids, nomadic rocks that wandered too close to Jupiter's immense gravity and were pulled into orbit long ago. Their irregular shapes support this. They are not massive enough for their own gravity to pull them into a round shape, so they retain the rough, fractured appearance of a typical asteroid. But the story is not that simple. Some of these moons, particularly those orbiting in the same direction as Jupiter's rotation, the prograde group, share similar surface colors and compositions. This suggests they might be fragments of a much larger, single body that was shattered in a cataclysmic collision, a moon that formed alongside Jupiter only to be blasted apart. Other groups, especially those orbiting backwards in a retrograde direction, are more diverse, hinting at multiple capture events from different parts of the asteroid belt. Their orbits are a tangled mess, often highly inclined and eccentric, crossing paths in ways that seem destined for future collisions. These chaotic dances are not stable over billions of years. They are the lingering turmoil of a system still settling from its violent birth. So are these moons primordial building blocks that never coalesced into something larger, or are they the shattered debris of ancient, forgotten worlds that once circled the king of planets? Their jagged silhouettes and wild orbits are a cryptic archive, holding clues to a time of colossal impacts and gravitational piracy that shaped the entire Jovian neighborhood. The violent chaos of Jupiter's captured moons pales before the systematic, relentless fury of its closest large satellite. Jupiter's moon Io is a world on fire, a global forge of volcanic rage that makes Earth's most active regions look dormant. Its surface is a cracked, sulfur-stained canvas painted with over 400 active volcanoes, constantly erupting with plumes that can reach hundreds of miles into space. This makes Io the most volcanically active body in the entire solar system, a title it holds with terrifying authority. The sheer scale of this activity presents a fundamental mystery. What could possibly power such a global inferno on a world so small, a moon only slightly larger than our own? The answer lies not in radioactive decay in its core, as with Earth, but in an external gravitational engine of breathtaking violence. Io is caught in an orbital tug of war between the immense gravity of Jupiter and the rhythmic pulls of its neighboring giant moons, Europa and Ganymede. These moons are locked in precise orbital resonances. For every one orbit Ganymede makes, Europa completes 2 and Io completes 4. This celestial clockwork means Io is repeatedly stretched and squeezed by the competing gravitational forces, a process called tidal heating. Imagine taking a ball of clay and kneading it continuously in your hands. The friction from that constant flexing generates intense heat. On Io, this happens on a planetary scale, with its very interior being deformed by these tidal forces. The friction generated is so tremendous that it melts rock, creating vast reservoirs of magma that erupt violently through the thin, brittle crust. It is a world literally heated from the outside in, its fiery heart stoked by the gravitational dance of its celestial neighbors. Yet the precise mechanics of this heating remain an enigma. Scientists debate where exactly this tidal energy is being deposited. Is the heat generated uniformly deep within a partially molten mantle, or is it concentrated in a specific, flexible layer closer to the surface? The distribution of Io's volcanoes provides a clue, as they are not scattered randomly but seem to be offset from where the models predict the maximum heating should occur. This suggests the moon's interior is more complex than a simple, uniformly squishy sphere. An even more profound possibility is that Io does not just have isolated magma chambers, but hosts a global ocean of magma, a subterranean sea of molten rock sloshing beneath its crust. Some models and measurements of Io's magnetic field hint at this, suggesting the presence of an extremely hot, electrically conductive layer, consistent with a planet-wide magma ocean dozens of miles thick. If true, this would make Io's geology unlike anything else we know. A world with a liquid rock mantle, a crust that is constantly being recycled by volcanic plumes, and a heat source that is written in the orbits of the moons above. The volcanoes of Io are not just geological features, they are the visible exhaust ports of a gravitational engine, a testament to the fact that in the Jupiter system, even a moon's internal fire is controlled by the intricate clockwork of the heavens. While Io burns with volcanic fire, its neighboring moon Europa conceals its potential for life beneath a shell of serene ice. This is not a dead, frozen world. Beneath a cracked and fractured crust of water ice, perhaps 10 to 15 miles thick, scientists are now virtually certain a global ocean exists. The evidence is compelling and comes from multiple lines of investigation. Spacecraft imagery shows a surface crisscrossed with dark streaks and ridges, a landscape that looks like a cracked eggshell. This suggests the ice is geologically active, shifting and renewing itself, likely driven by the tidal flexing from Jupiter's gravity, much like Io but with water instead of rock. The most definitive clue, however, came from the Galileo spacecraft's magnetometer. As Galileo flew by Europa, it detected a subtle but distinct magnetic field induced within the moon itself. This field wobbled in sync with Jupiter's powerful one. The only plausible explanation for this behavior is a large, global layer of electrically conductive fluid beneath the surface. On Earth, such a conductor is our planet's molten iron core. On Europa, the prime candidate is a salty, global ocean. This is not a small sea. Current estimates suggest Europa's hidden ocean contains more than twice the volume of all Earth's oceans combined, a vast, dark abyss sealed under ice. This revelation transforms Europa from a frozen curiosity into one of the most promising places to search for life beyond Earth. Where there is liquid water, energy from tidal heating, and likely a rocky seafloor where water and minerals interact, the basic ingredients for biology as we know it could be present. But how could we ever probe an ocean buried under miles of solid ice? Nature may have provided us with a backdoor. The Hubble Space Telescope has on several occasions observed what appear to be sporadic plumes of water vapor erupting from Europa's south polar region, towering over 100 miles above the surface. These are not confirmed beyond all doubt, but the observations are tantalizing. If real, these plumes would be like geysers, venting material from the subsurface ocean or from pockets of water closer to the surface directly into space. This presents an extraordinary opportunity. A future spacecraft could fly through one of these plumes and analyze its composition with sophisticated instruments, tasting the chemistry of Europa's hidden ocean without ever having to land or drill. What might it find? Simple organic molecules are a strong possibility. Evidence of hydrothermal vents on the seafloor, similar to those on Earth that teem with life, would be revolutionary. Or, in the most profound scenario, it could detect signatures that are unmistakably biological. The mystery of Europa's ocean is no longer just about whether it exists, but about what lives within it. These fleeting plumes are our potential key to answering that ancient question. Are we alone in the universe, or is life a common miracle wherever the conditions are right? Europa's plumes are a tantalizing hint, but its larger sibling holds a distinction no other moon can claim. Ganymede is not merely Jupiter's largest satellite. It is a world larger than the planet Mercury, a moon so massive it possesses its own intrinsic magnetic field. This is a feature shared only with planets like Earth and Mercury in our solar system, a self-generated bubble of magnetism that carves out a tiny magnetosphere within Jupiter's overwhelming one. For scientists, this was a stunning discovery. A magnetic field is the signature of a dynamic, churning interior. On Earth, ours is generated by the convection of molten iron in the outer core. For a moon to have one suggests a similar hidden engine. The leading theory is that deep within Ganymede, pressures and temperatures are still high enough to keep a layer of iron-rich liquid churning. This would require a core that has remained hot and molten for billions of years, a significant feat for a body that is not subjected to the intense tidal heating that scorches Io. The heat may be a leftover from Ganymede's formation, a primordial warmth that has been slow to escape through its icy exterior, or it could be supplemented by a gentler form of tidal flexing from Jupiter's gravity. This internal dynamo creates a magnetic field that interacts directly with Jupiter's own in a complex dance. During its orbit, Ganymede's magnetosphere opens and closes, creating brilliant auroral ovals at its poles that flicker and change in ways that revealed an even greater secret. Observations from the Hubble Space Telescope and data from the Galileo spacecraft showed these auroras were not behaving as they should if Ganymede were a solid ball of rock and ice. Their subtle rocking could only be explained if a large, global, electrically conductive ocean existed beneath the surface. The salt water in this ocean, much like the one on Europa, interacts with Ganymede's magnetic field, creating a secondary induced field that tugs on the auroras. The evidence points to a remarkable interior architecture, a layered world with a metallic core, a rocky mantle, and then a vast ocean of liquid saltwater sandwiched between two distinct layers of ice. The top layer is the familiar water ice crust we see. Below the ocean, scientists believe there is a second, thicker layer of ice, but under such immense pressure that it forms exotic high-pressure ice phases, possibly with the consistency of hot, slushy rock. This makes Ganymede a cosmic club sandwich of ice, water, and rock with a liquid iron heart. This subsurface ocean, potentially containing more water than all of Earth's oceans combined, resides in a stable environment protected by a thick icy roof. With a heat source from the core below and likely contact with a rocky seafloor, Ganymede joins Europa as a prime candidate in the search for extraterrestrial life. The mystery here is one of scale and persistence. How does a moon maintain both a molten metal core and a liquid water ocean over the age of the solar system? Ganymede is not just a moon, it is a miniature planet with a hidden, layered ocean, proving that even in the shadow of a giant, worlds of profound complexity can thrive. Ganymede's complex, layered world stands in stark contrast to the battered relic orbiting just beyond it. Callisto, Jupiter's second-largest moon, presents a face frozen in time. Its surface is the most heavily cratered landscape in the entire solar system, a record of impacts spanning billions of years with no geological activity to erase them. Each crater lies upon older craters, creating a scene of utter stillness, a fossil from the solar system's violent youth. This ancient, unbroken crust screams of a geologically dead world, a moon that cooled off and shut down eons ago. For decades, that was the accepted story. Callisto was a simple ball of ice and rock, a cold museum of cosmic collisions. Then the Galileo spacecraft flew by and measured the moon's magnetic field. Just as with Europa and Ganymede, the data revealed a subtle, induced magnetic signature. Once again, the most logical explanation was a hidden layer of electrically conductive fluid, a subsurface ocean of salty water. This finding sent shockwaves through planetary science. How could a moon that looks so utterly inert, a world with no volcanoes, no shifting tectonic plates, and no significant tidal heating from Jupiter, possibly maintain a liquid ocean over the age of the solar system? Callisto does not experience the intense gravitational kneading that fuels Eo's volcanoes or warms Europa's interior. Its orbit is farther out, and it is not locked in the same orbital resonance with its siblings. The heat from its formation should have leaked away into space long ago. So what mysterious furnace is keeping this buried sea from freezing solid? The answer may lie not in intense heat, but in perfect insulation and a powerful antifreeze. Scientists theorize that Callisto's ocean is not in direct contact with a rocky mantle below, as is suspected on Europa. Instead, it might be sandwiched between two thick layers of ice. The top layer is the ancient cratered crust we see. Below the ocean, there could be a deeper layer of high-pressure ice forms, exotic ices that behave more like hot, slushy rock under immense pressure. This insulating blanket of ice above and below could trap what little primordial heat remains with remarkable efficiency. Furthermore, the water itself is likely not pure. It is almost certainly a brine, saturated with salts like magnesium sulfate or ammonia. These compounds act as potent antifreeze, dramatically lowering the freezing point of the water. A combination of residual internal warmth, superb insulation, and a chemical recipe that resists freezing might just be enough to maintain a sluggish, deep ocean in a state of cold, slow slush for billions of years. Callisto's mystery forces us to rethink the very requirements for liquid water in the outer solar system. It suggests that oceans may not need a fiery, dynamic heart to survive. They can persist in quiet, frozen tombs, kept liquid by chemistry and insulation in a state of suspended animation. This expands the possible abodes for life dramatically, implying that even the oldest, most battered worlds might cradle hidden, dark seas where unknown processes slowly unfold in the eternal cold. Yet the serene, frozen potential of Callisto stands in stark contrast to a dazzling and dynamic feature closer to Jupiter's cloud tops. Draped around the planet's southern hemisphere is a celestial ornament of breathtaking precision known as the String of Pearls. This is not a single storm, but a chain of massive, rotating white ovals, each a colossal anticyclone larger than our largest hurricanes, strung together in a near-perfect, evenly spaced formation. From space, they look exactly like their name suggests, a luminous necklace of giant pearls, each one a vortex of swirling, bright white clouds set against the darker bands of Jupiter's atmosphere. This stunning arrangement was captured in magnificent detail by the Cassini spacecraft as it flew past Jupiter on its way to Saturn, revealing a meteorological marvel that combines immense power with delicate order. The formation of these white ovals is a story of atmospheric mergers and survival. They are believed to be the descendants of smaller storms that formed in the turbulent shear zones between Jupiter's powerful jet streams. Over time, through a process scientists call vortex merger, smaller similar storms can drift together, combine, and stabilize into a larger, more powerful oval. What is truly remarkable about the String of Pearls is not just their individual size, but their collective behavior. Unlike the chaotic tangle of storms we might expect, these giants maintain a respectful distance from one another. They do not merge, nor do they drift apart. For decades, observations have shown them rotating in place, evenly spaced along their atmospheric lane, a synchronized dance of atmospheric titans. This neat, bead-like formation poses a fascinating fluid dynamics puzzle. On a planet with no solid continents to disrupt flow, what keeps these massive vortices in such a perfect lineup? The answer likely lies in the concept of atmospheric spacing, or the staircase model. Imagine placing several large stones in a flowing stream. The water will part around each stone, creating a series of alternating currents and calm zones downstream. On Jupiter, each giant white oval acts as one of these stones in the river of the planet's fast-moving jet stream. The storms create zones of influence around themselves, areas of altered wind flow and pressure. When multiple such storms exist in the same band, these zones of influence can interact, effectively creating invisible barriers that prevent the storms from getting too close. They become locked in a stable configuration, repelling each other through fluid interactions rather than colliding. The even spacing is the natural equilibrium point where these repulsive forces balance the flow of the background winds. It is a self-organizing system where chaos gives birth to a temporary, beautiful order. This phenomenon shows us that Jupiter's atmosphere is not just a realm of random violence, but one where patterns can emerge and persist, crafting temporary artworks of storm and wind on a scale that dwarfs our entire world. How long will this particular necklace last before the pearls drift or merge, creating a new mystery for future observers? That beautiful necklace of storms is a surface decoration on Jupiter's most fundamental feature, its stripes. Those alternating dark belts and bright zones are the planet's iconic signature, painted across its face in bands of tan, orange, white, and brown. For centuries, we saw them as a kind of atmospheric wallpaper, a two-dimensional pattern on the cloud tops. The true mystery lies in the third dimension. How deep do these bands actually go? Are they just skin-deep weather, or do they reach down into the planet's very heart? The Juno spacecraft provided a startling answer by peering beneath the clouds with its microwave radiometer and gravity science instruments. It found that the east-west jet streams defining these belts and zones are not shallow currents. They are planetary-scale rivers of gas plunging an astonishing 1,900 miles, or about 3,000 kilometers, into the abyss. That is roughly 1% of Jupiter's radius, a depth comparable to the width of the entire United States. This discovery shattered the old idea of Jupiter's weather as a thin, turbulent veneer. The stripes are not just painted on, they are carved into the planet's fluid interior by forces of immense power. Yet this answer only deepens the core mystery. What is generating these jet streams, and why do they stop at that particular depth? One leading theory suggests they are the surface expression of deep-seated convection. Imagine Jupiter's interior as a pot of thick soup simmering on a stove. Heat from the planet's core causes vast columns of warmer gas to rise while cooler gas sinks. On a rapidly spinning planet like Jupiter, the Coriolis force channels this up and down motion into powerful east-west flows, organizing those rising and falling columns into the parallel bands we see. In this view, the belts and zones are the tops of planet-wide convection cells, with the dark belts being regions where air is generally sinking, and the bright zones where air is rising, forming high-altitude ammonia ice clouds. However, Juno's gravity data presents a complication. The jet streams appear to fade out at that 1,900-mile mark, not continuing all the way to the metallic hydrogen layer. This suggests there might be a fundamental transition deep within Jupiter's fluid envelope, a boundary where the dynamics change. Perhaps the interior below that depth rotates as a rigid body, like a solid ball, while the atmosphere above it is free to shear and flow in these distinct bands. Some scientists propose this could be due to a change in the physical properties of hydrogen itself, from a molecular gas to a state where it behaves more like a liquid metal, suppressing the turbulent motions that drive the jets. Others wonder if powerful magnetic fields deep inside are acting as a brake, damping out the fluid motions and creating a calm layer below the storm. The stripes of Jupiter, therefore, are more than a pretty pattern. They are a window into the hidden machinery of a gas giant, a visible trace of a titanic heat engine churning thousands of miles below. Their depth reveals a planet divided into layers of motion, but we still do not know what draws the final line, what force tells the raging storms, you can go no further. But the planet's deepest atmospheric rivers are not the only forces sculpting Jupiter's polar skies. There, a different kind of light show rages with a ferocity that dwarfs our own northern lights. Jupiter's auroras are not fleeting curtains of green and red. They are permanent, planet-sized rings of radiation hundreds of times more energetic than Earth's, and they operate on a fuel source unlike any other. While Earth's beautiful displays are sparked primarily by particles from the solar wind, Jupiter's are powered by a dual engine. Yes, the solar wind contributes, but the primary driver is something far more exotic, material ripped from its volcanic moon, Io. Io's relentless eruptions spew sulfur and oxygen ions into space, where they become trapped by Jupiter's immense magnetic field. This creates a vast, donut-shaped cloud of plasma, a ring of charged particles called the Io plasma torus. Jupiter's magnetic field lines act as colossal highways, funneling this ionized material at tremendous speeds down into the planet's polar regions. When these particles slam into the upper atmosphere, they collide with hydrogen molecules, transferring energy and causing them to glow in brilliant ultraviolet hues invisible to our eyes. This process creates the main auroral oval, a constant, luminous necklace around each pole. Yet this established story is now filled with strange new twists. The Juno spacecraft discovered these auroras often pulse with unexpected regularity. brightening and dimming every few tens of minutes like a cosmic heartbeat. The cause of this steady pulsation remains unknown. It could be driven by vibrations within the planet's magnetic field itself or by periodic surges of particles from the plasma torus. Even more bizarre are the so-called detached auroras. These are luminous patches and swirls that appear disconnected from the main rings, floating separately in the polar darkness. They seem to be linked to interactions with the solar wind in unexpected ways, perhaps where Jupiter's magnetic field is compressed or reconfigured, creating isolated pockets where particles can rain down. The most astonishing mystery, however, is the sheer power of these lights. Jupiter's auroras generate not just visible and ultraviolet light, but intense bursts of X-rays. These are not mere glimmers, they are colossal X-ray flares containing hundreds of gigawatts of power, more than all of Earth's electrical consumption at any given moment. The mechanism for creating such energetic emissions is a major puzzle. On Earth, X-ray auroras are rare and linked to highly energetic electrons. On Jupiter, the primary suspects are heavy ions like oxygen and sulfur from Io, being accelerated along magnetic field lines to incredible speeds before crashing into the atmosphere. But the exact process that can accelerate these particles to such extremes is still a subject of intense debate. These auroras are more than a pretty light show. They are a direct readout of the violent, complex relationship between Jupiter, its magnetic fortress, and its volcanic moon. They illuminate a transfer of matter and energy on a scale we can barely comprehend, where a moon's fire paints the sky of a giant with X-rays. What other secrets are encoded in the pulsating, detached glow of these eternal polar lights? Those brilliant auroras are fueled by a moon that was itself a cosmic wanderer, captured by Jupiter's gravity in the distant past. This gravitational dominance extends far beyond its immediate moons, shaping the architecture of the entire solar system. Leading and trailing Jupiter in its orbit around the Sun are two colossal swarms of ancient asteroids, known as the Trojan asteroids. They are not orbiting Jupiter directly, but are instead trapped in gravitational parking spots called Lagrange points, specifically the L4 and L5 points. These are regions where the combined gravitational pulls of the Sun and Jupiter create stable zones like eddies in a flowing river. One swarm orbits 60 degrees ahead of Jupiter, the other 60 degrees behind, forever locked in a celestial convoy with the giant planet. These are not just a few rocks. Each swarm contains thousands, possibly millions of objects, making them a vast reservoir of primordial material. Their very existence and stability are a given, but their origin is one of the great enduring puzzles of our solar system's early days. Where did this immense population of Trojans come from? Are they pristine leftovers from the very region where Jupiter itself formed? Ancient building blocks that were swept into these stable points as the young planet migrated through the protoplanetary disk? Or are they captured intruders, objects that formed much farther out in the cold reaches of the solar system, beyond Neptune, and were later herded inward by shifting planetary orbits and trapped by Jupiter's gravity? Their composition holds the key. If the Trojans are made of the same dark, carbon-rich material as many asteroids in the main belt between Mars and Jupiter, it would suggest a local origin. But if they are icier, more akin to the frozen bodies found in the Kuiper belt, it would point to a distant birthplace and a dramatic journey inward. This is the core mission of NASA's Lucy spacecraft, the first mission ever sent to explore these ancient swarms. As Lucy flies by multiple Trojans throughout this decade, its instruments will analyze their color, composition, density, and geology. Early data has already delivered surprises, showing that some Trojans are far more complex than expected, with moons of their own and surfaces that suggest a rich and varied history. Unlocking the Trojan mystery is like opening a time capsule from the solar system's first few million years. These asteroids were witnesses to the giant planet's chaotic dance as they settled into their current orbits. They may contain organic compounds and water ice that were delivered to the inner planets, including Earth. By understanding whether the Trojans are native to Jupiter's neighborhood or captured immigrants, we will rewrite the story of planetary migration and learn what raw materials were present at the birth of our largest world. Are these silent rocks the original foundation of Jupiter, or are they refugees from the frozen edge of everything? Jupiter's furious spin is the engine behind its very shape. A day on the giant planet lasts a mere 9 hours and 56 minutes, a dizzying rotational speed that makes it the fastest spinner in our solar system. This incredible velocity has profound physical consequences, flattening the planet at its poles and bulging its equator in a dramatic way. Astronomers call this oblateness, and Jupiter is the most oblate planet we know, looking less like a perfect sphere and more like a slightly squashed beach ball someone has squeezed at the top and bottom. This shape is a direct and permanent imprint of its rapid rotation, a centrifugal force constantly trying to fling its gaseous body outward. But the mystery lies not in the bulge itself, but in what this relentless spin does to the planet's hidden interior and the powerful forces it generates. That centrifugal force influences everything, starting with the planet's deep structure. The rapid rotation organizes the chaotic convection within Jupiter's fluid interior. It acts like a cosmic egg beater, channeling the upwelling and downwelling of hot and cold material into the distinct bands and zones we see as stripes on the surface. Without this spin, Jupiter's atmosphere might be a turbulent, featureless soup. Instead, the rotation sculpts the chaos into a semblance of order, creating the parallel jet streams that plunge thousands of miles deep. This spinning also likely plays a crucial role in the generation of Jupiter's monstrous magnetic field. The dynamo that creates this field occurs within the planet's layer of metallic hydrogen, where electrically conductive fluid is in motion. Jupiter's rapid rotation organizes and amplifies these motions, turning that churning metallic sea into a far more efficient dynamo than a slower spinning planet could ever produce. It is the spin that supercharges the magnetic engine, creating a field so vast it dwarfs the Sun itself. Yet for all we understand in principle, the precise interplay between spin, internal structure, and weather remains a monumental challenge to model. Computer simulations of gas giants must account for the Coriolis effect on a staggering scale, where every movement of fluid is deflected by the planet's whirl. This complexity means small changes in how we model the depth of the jet streams or the viscosity of the interior can lead to wildly different predictions. The rapid rotation creates atmospheric phenomena with no earthly equivalent, like the stable geometric polygons at the poles. It influences how heat is transported from the deep interior to the cloud tops, and how storms like the Great Red Spot maintain their coherence against the shearing winds. We are essentially trying to simulate a fluid universe with its own unique physics, a task that requires some of the most powerful supercomputers on Earth and still yields surprises with every new Juno data drop. Jupiter's shape is a simple clue to a deeply complex truth. Its spin is the heartbeat of the entire system, a rhythm that sets the tempo for everything from its magnetic fury to the dance of its eternal storms. Jupiter's rapid spin creates a world of stark contrasts where light and shadow play out on a planetary stage with surprising consequences. When one of Jupiter's large moons, like Ganymede or Io, passes in front of the Sun, it casts a profound shadow onto the churning cloud tops below. These are not the gentle, cooling shadows of a tree on a summer day. These are hot shadows. Remarkably, infrared observations have revealed that these dark patches on Jupiter are actually warmer than the brightly lit areas surrounding them. This is a complete reversal of our everyday intuition, where shade provides relief from the heat. The explanation lies not in the shadow itself, but in what happens when sunlight is suddenly blocked. Jupiter's upper atmosphere is normally heated from above by the Sun and from below by the planet's own immense internal warmth. The visible cloud layer we see is cold, dominated by ammonia ice crystals at temperatures around -200 degrees Fahrenheit. When a moon's shadow sweeps across this region, it instantly removes the solar heating. You might expect the temperature to plummet. Instead, it rises. Scientists believe this happens because the shadow disrupts the delicate thermal balance. Without sunlight, the topmost layer of ammonia ice clouds cools rapidly. But this cooling might have two counterintuitive effects. First, the sudden chill could make the upper air denser, causing it to sink. This sinking motion would then allow warmer, denser air from deeper, hotter layers of the atmosphere to well up to fill the void, bringing its heat with it to a level our instruments can detect. It is like lifting a lid off a simmering pot, allowing the steam to rise. A second possibility involves atmospheric chemistry. Sunlight drives chemical reactions that create the haze of particles in Jupiter's upper atmosphere. In the darkness of a shadow, those reactions stop. This could cause the haze particles to shrink or disappear, making the atmosphere more transparent. With this clearer window, infrared instruments can then peer deeper than usual, sensing the warmer layers that are always present below the cold cloud tops. The shadow does not create heat, it simply pulls back the curtain, revealing the planet's internal furnace. This phenomenon is a perfect example of how Jupiter constantly defies our Earth-based expectations, turning a simple concept like a shadow into a complex probe of its hidden, layered atmosphere. What other secrets might be revealed in these fleeting patches of darkness? The shadow's fleeting warmth is a testament to Jupiter's layered complexity, a quality mirrored in the strange architecture of its family of moons. When we look at the Jovian system, we see a striking gap in the lineup. There are the four giant, world-sized Galilean moons, each a geological wonder. Then there is a vast collection of dozens of small, irregular satellites, most no larger than a city. What is conspicuously missing are the intermediate-sized moons, worlds perhaps a few hundred miles across that should logically exist between these two extremes. This absence is not just a curiosity, it is a direct challenge to our models of how moon systems form around giant planets. According to the leading theory of satellite formation, a gas giant like Jupiter is born from a swirling disk of gas and dust, much like a miniature solar system. As the young planet coalesced, its surrounding material flattened into a circumplanetary disk. Within this disk, moons would have accreted, growing from dust grains into larger bodies. The process should have naturally produced a full spectrum of sizes, from pebbles to planet-sized spheres, with many mid-sized objects forming in the gravitational sweet spots between the growing giants. Yet today, that middle class is almost entirely absent. Where did they go? One compelling and violent theory is that they were simply destroyed. The early Jovian system was a chaotic shooting gallery. With so many objects sharing similar orbits, catastrophic collisions would have been frequent. A moon a few hundred miles in diameter, if struck by another of similar size, would not merely be cratered, it could be completely shattered. The debris from such an apocalyptic event might have then been reaccreted into the smaller, irregular moons we see today, or perhaps even contributed to Jupiter's faint rings. The fragments that did not escape would have eventually spiraled inward and been consumed by the planet's gravity. Another possibility is that these intermediate moons never formed in the first place. The gravitational dynamics within the circumplanetary disk may have been too turbulent, with the powerful tug of the growing Galilean moons disrupting the orderly accretion of material in the zones between them. It is like trying to build a sandcastle in the surf. The waves from the larger structures constantly wash away any intermediate formations before they can solidify. A third, and perhaps most dramatic, scenario is ejection. Jupiter's gravity is a powerful slingshot. As the large moons migrated into their current stable orbits billions of years ago, their gravitational interactions could have flung any mid-sized neighbors clear out of the Jovian system entirely, sending them hurtling into interstellar space or into orbits around the Sun. These lost moons would now be anonymous asteroids or dormant comets, their true origin story forgotten. This missing middle class forces us to reconsider the early days of our solar system as a time of far greater violence and instability than we often picture, where entire worlds were born only to be annihilated or exiled before they could ever find a stable home. Beneath the swirling tapestry of stripes and storms, Jupiter's atmosphere is a chemical labyrinth. The cloud decks are not a uniform blanket but a layered cake of exotic compounds, each with its own distinct color and profound mystery. From the cold, high-altitude hazes down to the deep, hidden realms, the precise recipe for Jupiter's palette remains one of its most stubborn secrets. Scientists have long mapped out a basic structure based on temperature and pressure. The highest, coldest clouds are believed to be made of white crystals of ammonia ice. Deeper down, where it is warmer, a second deck likely forms from ammonium hydrosulfide, a compound that might give rise to the tawny browns and tans. Deeper still, where pressures and temperatures climb further, there should be clouds of water ice and perhaps even droplets of liquid water. This three-layer model is elegant in theory, but the reality observed by probes like Juno is far messier and more intriguing. The colors do not conform neatly to these predicted layers. Brilliant white plumes erupt in dark belts and deep red stain zones that should be pale. Something is actively painting the atmosphere with pigments we do not fully understand. The whites are the simplest, likely just fresh ammonia ice crystals lofted high by upwelling winds. The rich browns and oranges, however, point to more complex chemistry. When ultraviolet light from the sun or powerful lightning strikes hit the cloud decks, it can break apart molecules like ammonia and hydrogen sulfide, allowing their fragments to recombine into new, more complex compounds. These photochemical reactions, acting over centuries, could be creating a cocktail of sulfur-bearing molecules and complex hydrocarbons that impart the darker hues. It is a planet-wide chemistry set simmering under the harsh radiation of space. Yet the deepest enigma of color is reserved for the king of storms itself. The Great Red Spot's iconic brick red hue is its most famous feature, and its origin is perhaps the greatest chemical puzzle on Jupiter. What compound exactly is responsible for that persistent crimson? The most promising suspects are chemicals containing phosphorus or sulfur. One leading theory suggests that the storm's powerful upwelling acts like a mining operation, dredging material from deep, hot layers where phosphorus exists as a gas called phosphine. As this phosphine rises into the cold, high-altitude sunlight of the spot, ultraviolet radiation could break it apart and reassemble it into red-colored compounds like red phosphorus or even more complex molecules. Another compelling idea involves sulfur. Deep within the atmosphere, sulfur likely exists in compounds like hydrogen sulfide. The intense turbulence and possible lightning within the Great Red Spot could provide the energy to cook these sulfur compounds into long chains, creating reddish polymers. Think of it as the planetary equivalent of caramelizing sugar. Applied heat and chemistry transform a clear substance into a rich, deep color. The true answer remains elusive because we cannot yet sample the spot's clouds directly. Its color even fluctuates over time, deepening and fading in ways that suggest an active, dynamic chemical process is at work, not a static stain. Is the red a sign of the storm's health, a byproduct of its immense energy, or is it a fleeting chemical signature, a color that appears only under the perfect storm of conditions found within that ancient vortex? The clouds of Jupiter are more than weather. They are a canvas upon which alien chemistry writes in colors we are still learning to decode. That alien chemistry is a record of the planet's own epic journey, a voyage that reshaped the entire solar system. Jupiter did not simply form in its current orbit and remain still. Planetary scientists now believe it went on a grand tour, a migration that scattered worlds and determined the fate of planets like our own. This idea is known as the Grand Tack hypothesis, and it paints a picture of the early solar system as a far more dynamic and violent place than we once imagined. The story begins with a young Jupiter, freshly formed from the primordial disk of gas and dust. According to the models, as Jupiter interacted with the remaining material in its path, it began to spiral inward, drifting closer and closer to the Sun. This migration was like a cosmic bulldozer, its immense gravity clearing a path and scattering the planetesimals, the building blocks of planets that lay before it. Jupiter may have ventured as far inward as the orbit of Mars is today, profoundly disrupting the formation process in the inner solar system. If it had continued, our solar system might look utterly different, with giant planets orbiting close to the Sun as we see in many exoplanet systems. But then Saturn entered the picture. As Saturn formed and began its own inward migration, it eventually caught up to Jupiter. The two giants became locked in a special gravitational configuration called a mean motion resonance. In this dance, for every 2 orbits Jupiter completed, Saturn would complete one. This resonant link created a powerful, combined gravitational influence that acted like a cosmic leash. Instead of allowing both planets to fall into the Sun, the resonance reversed their migration. The duo then moved outward together, with Jupiter settling into its current orbit and Saturn following to its present position. This grand tack, this inward journey and subsequent outward retreat, had staggering consequences. The inner solar system was left severely depleted of material, which could explain why Mars is so small. Its growth was stunted when Jupiter swept away much of its building supplies. The asteroid belt was violently sculpted, its population scattered and mixed, creating the strange distribution of rocky and icy asteroids we find there today. Most profoundly, this chaotic migration may have been the delivery mechanism for Earth's water. As Jupiter and Saturn moved outward, their gravity would have hurled countless icy planetesimals from the outer solar system inward, bombarding the young rocky world. These frozen comets and asteroids, rich in water and organic compounds, could have been the very source of our oceans and the ingredients for life. In this view, Jupiter's ancient wanderings were not a quiet process. They were a series of gravitational shocks that built the architecture of our planetary neighborhood and may have been the crucial event that made Earth a habitable world. The mystery we now face is confirming this epic tale. Does the precise composition of asteroids or the subtle orbital quirks of small bodies hold the definitive fingerprint of Jupiter's grand tack? That ancient gravitational journey placed Jupiter in a category all its own, leading to one final, profound question about its very nature. Is Jupiter a failed star? This captivating idea stems from a simple, striking fact. Jupiter's composition is almost a perfect match for the Sun. Both are made predominantly of hydrogen and helium, the same primordial gases that fuel the stars. If you could gather up about 80 Jupiters and crush them together, you would have enough mass to ignite the fires of nuclear fusion in its core, creating a small, dim red dwarf star. This comparison has earned Jupiter the nickname of a failed star, a world that gathered almost but not quite enough material to light up. The truth, however, is more nuanced and far more interesting. Jupiter is not a star that failed. It is a planet that succeeded spectacularly under a different set of cosmic rules. The critical difference lies in what happens at the core. Inside the Sun, the immense pressure from its own gravity crushes hydrogen atoms together with such force that they fuse into helium, releasing the staggering energy that makes stars shine. This process requires a minimum mass threshold, roughly 80 times the mass of Jupiter. Jupiter, magnificent as it is, falls dramatically short of this benchmark. Its core, whether fuzzy or distinct, is a place of immense pressure and heat by our standards, but it is a cold, dark quiet compared to the inferno of a stellar core. There is no sustained nuclear fusion happening there. Instead of a star, Jupiter is better understood as the king of planets, and the prototype for an entire class of objects that blur the line between worlds and stars. This boundary is inhabited by brown dwarfs. These are celestial objects more massive than Jupiter, but still too small to sustain full hydrogen fusion. They form like stars from collapsing clouds of gas, but they are essentially too puny to light the main engine. The smallest brown dwarfs can be only about 13 times more massive than Jupiter. In that murky zone between 13 and 80 Jupiter masses, these objects might briefly fuse a rare isotope of hydrogen called deuterium, or even lithium, giving off a faint, smoldering glow before cooling into planetary-like darkness. Jupiter, at just over 300 times the mass of Earth, sits definitively on the planetary side of this divide. It formed not from a collapsing cloud like a star or brown dwarf, but from the bottom up, accreting a core first and then gathering its gargantuan atmosphere from the solar nebula. So, while Jupiter shares the Sun's ingredients, it followed a completely different recipe. Calling it a failed star is like calling a mountain a failed planet. It misunderstands the process entirely. Jupiter is a triumphant planet, a gravitational anchor that may have guided the formation of our solar system and protected the inner worlds. Its grandeur does not come from the fire it lacks, but from the profound mysteries it holds within its swirling, stormy heart. Jupiter stands as a testament to the beautiful incompleteness of our knowledge. From the churning fury of its great red spot to the silent, dark oceans beneath Europa's ice, each mystery pulls back a layer to reveal even deeper questions. We have navigated its lopsided magnetic fortress, pondered its dissolved core, and witnessed the alien chemistry painting its clouds. We have seen how its ancient migrations may have built our solar system, and how its rapid spin shapes its very being. These 25 puzzles are not mere gaps in a chart. They are beacons guiding the next generation of explorers, scientists, and dreamers. Every unanswered question is an invitation, a reason to build a new spacecraft, to point a more powerful telescope, and to refine our theories of how worlds are born and live. The giant next door is no longer just a bright dot in the sky. It is a dynamic, roaring, complex kingdom, a constant reminder that the universe is far stranger and more wonderful than we can often conceive. So we turn the curiosity back to you. Which of Jupiter's mysteries captured your imagination the most? Was it the eternal storm, the hidden oceans, or the possibility of a planetary history written in wandering asteroids? Let us know in the comments below. If you enjoyed this journey through cosmic puzzles, be sure to subscribe for more explorations into the deepest mysteries of space. And tonight, or the next clear night you have, take a moment to look up, find that steady, brilliant light. See it not just as a planet, but as a world of endless storm and silent seas, a colossal neighbor whose secrets are waiting one by one to be unveiled.